Hello, in this video I'm going to continue my lessons on elementary number theory. This is lecture number 3 and this is part 4 of the topic of divisibility. Again, in this lecture I want to present one theorem which is very simple but very useful in elementary number theory and present a few examples with the detailed solutions. And then at the end of the video, as is usual for the videos on this playlist, I present you with a PDF file. I will put the link of this PDF file, which are exercises designed based on the material on this topic, on this lecture and the previous lectures, with the main focus on the material for this lecture, of course, so that you can practice and improve your skills if you have time and you are interested in doing that. And then after this lecture is finished, I will solve all those problems. Each video that I will produce will contain the detailed solution of those problems. One video, one problem, and then after those problems, I will continue my lectures in elementary number theory. Okay, so now let us go to the first topic of today's lesson. I will start with a definition. So the definition is the definition of linear combination. Let B and C be, okay, one of these B's are extra. Let B and C be integers, then MB plus NC, where M and N are integers, is called a linear combination of B and C. Okay, so that is the definition of what we call a linear combination of two integers in number theory. So if I want to give you examples, okay, so let B and C be integers, then all the numbers in this list are actually special cases of linear combinations of B and C. For example, B itself is also a linear combination. So let me go to the board. If I have B and C integers, if I ask you to write a linear combination of these two numbers, it means pick up two integers, which we call them M and N, whatever you want to, multiply the first one by the first one, multiply the second one by the second one, and add the results. What you get is called a linear combination of B and C. Of course, I have infinitely many linear combinations of B and C because I have infinitely many choices for integers M and N. So, for example, if I choose, let me write this linear combination MB plus NC in front of your eyes. So, for example, if I choose M to be 1 and N to be 0, this linear combination will just give me B. So, B is indeed a linear combination of B and any other integer in this way. You have to view it in this way. So, B is a linear combination of B and C. For the same reason, C itself is also a linear combination of C and any other number. Yes, you can write it as 0B plus 1C. For example, is B plus C a linear combination? Yes. Here I choose 1 for M, I choose 1 for, so let me write, B plus C can be viewed as 1B plus 1C. So B plus C is also linear combination. What about B minus C? That's also correct. Why? Because I choose 1 for M and I choose minus 1 for N. B minus C is also a linear combination. For example, I can choose M to be 4 and N to be minus 3. Of course, we do not write 4B plus or minus. That is exactly a linear combination as well. So this is the reason that all the numbers in this list are called linear combinations, and two very important special case are B plus C and B minus C, the sum and the difference of the integers. Okay, now let us go to the theorem for this lesson. If two integers are divisible by a given integer, then any linear combination of these two integers is also divisible by that integer. Okay? So in other words, if A, B, and C are integers such that B is divisible by A and C also is divisible by the same A, then any linear combination of B and C, MB plus NC, is also divisible by the same number A. So the first thing that we want to do is now to have a proof for the theorem. So what I have in my hand, I know that A divides B is granted, and, this means and. I know that A divides C is also granted, and they have given me two arbitrary integers, M and N. I want to show that if I construct this linear combination MB plus NC, this is definitely divisible by the same number A. Okay, so let me see if I'm recording everything. Yes. Okay, so now how can I prove that? Okay, when you say A divides B, according to the definition of divisibility, I can grant the existence of a Q in Z such that the number on the right B is the number on the left multiplied by that Q. That's the definition of A divides B. For the same reason, when you say that A divides C, I can grant the existence of an integer, probably not the same integer, so let me call it Q prime, in Z such that the number on the right is equal to the number on the left multiplied by Q prime. So these are granted because you have granted these two statements for me. Now I want to say something about NB plus NC and its divisibility relation to the old number A. Because I see NB plus NC, this motivates me to construct NB plus NC from these equalities that I have. So it is not hard to motivate yourself to multiply both sides by M. So this becomes MB is equal to MAQ, and this one I multiply by N, so it becomes NC is equal to NAQ prime. And because I want the sum of these two, it motivates me to add them up. When I add them up, the left-hand side becomes MB plus NC, and the right-hand side, when I want to add them up, you see that I have a factor A in common, so it motivates me to pull it out because I want to say something about divisibility by A. Then what is left for me in the pair of brackets is MQ plus NQ prime. But what type of number is this number? M and N are given to be integers. Q and Q prime are also integers by the definition of divisibility. So this means that this combination, which is a product, which is the sum of the product of integers, is also an integer. So if you don't mind, let me call it capital Q. But what is important is that this capital Q belongs to the set of integers. So this means that MB plus MC, which is an integer, is equal to A times another integer. So this means this number divides this number. So I can conclude that A divides MB plus NC. And this was just the elementary proof. Okay, but let us now solve some examples and then end this lesson. Okay, so what are the examples? The first example that we want to do here is let A, B, and B, X, and Y be integers such that N divides X minus A and N divides Y minus B. We want to show that, okay, N also divides XY minus AB. So now let us go to the board and do it. Okay, so we want to do this one. As I told you that in these lectures, the solution that I present are based on the theorems and material that I covered in my own lectures. By no means I am claiming that the way that I am doing is the only way, but might be that is an optimal way if you want to do things faster. Okay, so it is granted that two different integers are both divisible by the same integer. Okay, I want to prove that this combination is also divisible by the same integer. And I want to use the theorem that I actually just mentioned for you. Okay, so what can I do? I can say that when you are giving me that two numbers are divisible by the same number, any linear combination of these two numbers, according to this theorem, should be divisible by this number. So this motivates me. Can I write this number as a particular linear combination of these two numbers? Because if I could, then I am done. Yes? So and that is very simple because the algebra is extremely simple in this case. So I don't think you have hard time. So what I would say, I will multiply this number by y, motivated by the fact that I need xy somewhere. And I multiply this one by, say, let me multiply it by a. Okay? Let us see if it works. First of all, I want you to understand that what I have done is legitimate. It is possible. Why? Because y and a are integers. And if I ask you what I have written here, according to what I told you, you will tell me this is a linear combination of these two integers. This integer is multiplied by an integer, plus that integer is multiplied by another integer, and then I am adding them. So what you see here is a linear combination of these two. And I know that this is true because of the theorem I just showed. If two numbers are divisible by the same number, any linear combination of these two numbers, including this linear combination, is also divisible by that. So if you grant me these two based on this theorem, I can immediately write that one. Of course, I can write any linear combination, but any other linear combination will not be useful. So I have to choose wisely which linear combination I want to look at so that it will solve my problem. So that's the idea. Okay, but that algebra is very simple now. So let me just continue one step. I just multiply y in, so it becomes xy minus ay. I multiply a in, it becomes ay minus ab. So you see, the one that I chose was wise enough, because now this minus ay and that ay are cancelled, and what is left for me is xy minus ab. So this means that I can conclude that n divides xy minus ab. And that is exactly what I want to show. Okay? So again, I am not telling that this is the only way, but that is a good way. So you have to practice if you want to especially join mathematical competitions. You have to be very quick in seeing these patterns. Okay, let us go now to the next problem. The next problem, let a and n be natural numbers such that a divides 5n plus 3 and a divides 9n plus 4. Show that either a is 1 or a is 7. Okay, I can go to the board. If you want, you can pause the video and give it a try yourself. As usual, I insist, because you will not learn mathematics if you don't practice yourself. Okay? Okay, so we know that a divides this number and a also divides this number. We want to prove that a is either 1 or, this symbol means or, a is equal to 7. Okay, I want to use exactly the same theorem again, okay? So what I want to do, because I want to confirm that a is either 1 or 7, if you have watched the previous videos, you have some experience that it would be good if I have a constant number on the right-hand side. Okay, but I have 5n, and this one, the exercises that I solved for you previous to this lecture, was the ones that the left-hand side was also related to n itself, and then I told you how to eliminate n somehow that you can come up with a constant number on the right. But that method will not work here because the number on the left has nothing to do with the number n on the right. But instead, I have two pieces of information now. They are relating a and n together. Okay, so the idea is the same. So I want to come with some divisibility relation in which a is on the left, but on the right I have one single number. So this motivates me to get rid of this n. Okay, and then because the coefficient of n here is 5, the coefficient of n is there 9, I have to find a linear combination of these two so that n is indeed eliminated. Okay, so that is not very hard to see, yes? So I would say that from these two, I can conclude that a divides 9 times that plus minus 5 times that, which is a linear combination. First of all, I want you to understand that what I have done is correct. It's not wrong. Then we discuss if it is useful or not. Why this is correct? Because I know that two different numbers are divisible by the same number. So according to the theorem, any linear combination of those numbers, including this particular linear combination, is also divisible by a. Okay, I have infinitely many linear combinations of those numbers that I can write, but why on earth I have chosen this very particular linear combination? The idea is clear, because this becomes minus 45n and this becomes positive 45n, and it is aligned with my previous strategy to get rid of n. So that is why I have chosen these two particular numbers. So then what happens? This means that a divides 9, 5, this is 45n minus 45n, they are gone. 9 times 3 is 27, minus 20 is just 7. So a divides 7, and it is mentioned in the problem that a is a natural number. If a is a natural number and it's 7 divides that, there are only two choices for a. Either a is 1 or a is 7. Okay? One thing that you have to be careful about, this claims that if this is the case, A should be either 1 or 7. But it doesn't say that 1 and 7 are indeed realized. If you want to make sure that A equals to 1 can indeed happen, A equals to 7 can also indeed happen, you have to convince yourself by bringing some examples. So in other words, from these two, I know that there are two possibilities for A. 1 or 7. This analysis by itself does not grant that A is 1 is realizable and 7 is realizable. If you want to do that, you have to check it yourself. For example, if I choose n to be 1, then this gives me that A divides 8 and A divides 13. Okay, so the only number A that divides both of these numbers simultaneously is equal to 1. So yes, 1 is indeed realizable for some cases of n. What about 7? What about 7? If I choose 2, this becomes 13, this becomes 22. 13, 22 still A is 1. So is 7 indeed realizable? Yes. If you choose n to be 5, this becomes 25 plus 3, 28. And then that one becomes 49. Yes? And the only number that fits here, the only natural number that fits here is just 7. So yes, not only these are the only answers, but both of them are indeed acceptable because they are realizable under some conditions. Okay, now let us go to the next problem, which is of course the last problem as well. So here, let n be an integer. Show that n times n plus 1 times 2n plus 1 is divisible by 6. Okay, so let me write it on the board and then we can continue it, okay? Okay, so this is what we want to prove. 6 divides this combination. Okay? So the solution that I want to present here for you is just based on the theorem I just mentioned. So there will be different ways to really solve this problem, okay? But one way I want to use here, this depends on the theorem that I presented today and the one theorem from lecture 1. Okay, I will talk about that later. So what I will do is a little bit creative if you want to do it in this way that I'm talking about. This number 2n plus 1 can be viewed as n plus 2 minus, so let me write it, plus n minus 1, yes. So do you agree 2n plus 1 can be written as n plus 2 plus n minus 1 because n and n becomes 2n and 2 minus 1 is 1. But what is the benefit of that? This number on the left side that you see now can be viewed in this form. Instead of this, I would write n plus 2 plus n minus 1. Okay? And then I will multiply this here, plus I will multiply this here. So when I multiply this one here, I would write it as n times n plus 1 times n plus 2. But when I want to multiply it here, if you don't mind, let me write this on the left because I want to write them in their increasing order. So it doesn't matter, of course. It becomes this one times that one times this one. Okay? So now let me ask you one question. What is this one? This expression is a linear combination of this number and that number. Actually, this is the sum. Yes? The sum of two numbers is also one special case of the linear combination of those numbers. So, if I can show you this is divisible by 6, and if I can show you this is divisible by 6, in other words, if you call this one number B, if you call this one number C, if I can grant the truth of 6 divides B and 6 divides C, according to the theorem today we learned, we can grant that 6 divides B plus C and B plus C exactly this expression. So this is a question and that's a question, but these two questions have been answered in the first lecture. What was that theorem? I told you, I proved you that in that lecture, that if you have the product of k consecutive integers, that is divisible by k factorial. That was what I showed you in lecture number 1. Or probably 2, I don't remember exactly. But anyway, uh, here I have 3 consecutive integers. You see, this differ. This is one more than this is one more than this. So that's the product of 3 consecutive integers. So according to that theorem, it should be divisible by 3 factorial. Okay, so it is divisible by 3 factorial. But what is 3 factorial? 3 factorial is 3 times 2 times 1, which is 6. So it is guaranteed that b is divisible by 6. And now look, this is also a product of 3 consecutive integers. N minus 1, the next integer is n, the next integer is n plus 1. So that's also a product of 3 consecutive integers, and according to the same theorem, it is also divisible by 3 factorial, which is again 6. So we are done. So this means that this is granted, and this is also granted, and based on today's theorem, this 6 divides b plus c as a particular linear combination of b and c is also granted. And as I told you before, this is by no means the only way that you can do that. For example, one way of doing this, later we will see that we can prove that this is divisible by 2 and this is divisible by 3, and then we can use division algorithm, for example. Or we can also use modular arithmetic. But I am not jumping ahead of me because I want to follow my own structure in the number theory, but little by little, I hope that I will be able to cover everything that one person needs in elementary number theory in order to be able to understand the solutions of competition problems in mathematics. Okay, now before ending this video, let me show you the set of exercises that it would be useful for you to work them out before seeing the videos. And I will put a link for this in the description of this TikTok, but you know that that link is not a real link, but you can copy and paste it in your browser, and it will give you access to a PDF file containing these problems that I'm going to show you now. Okay, so let me fix everything. Yes, so these are problems. So there are 8 problems. Based on my own judgment, the first 2 are bronze level. So immediately you should be able to do them if you understand what's the content of the lecture. The 3, 4, 5, and 6 are silver level, a little bit higher level. And this one might be considered gold level, harder level. But of course, this level of difficulties are not comparable to the math competitions. I will probably finally make another playlist so that you will find more problems from real competitions, okay? But you have to prepare yourself, so you need to know all these material more or less very you have to be very skillful in these kinds of calculations in order to be able to solve harder level problems. Okay, so you can take a screenshot from here, and I told you that I will put the link on the description on TikTok video. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.